Lesson 4. Behavior Models. In this lesson, we will review state sequences, the purpose of transitions, and the 6 types and functional hierarchies that we can use to describe complex systems. Once again, recall that a state represents a snapshot of a system at an instant in time. We describe a state as the properties, values, and connections of the structural elements of a system at a given point in time. Recall also that a function is described by a beginning state, the state at which the system starts, and an objective state, which describes the system after the function. But a system can go through many states between the beginning and objective states. Indeed, understanding all of those in between states and how a system moves from one to the next is the purpose of the behavior model. The purpose of behavior models is to provide a step-by-step explanation of how a function is achieved. That is, a behavior model describes how a system changes from the initial state to the objective state. But systems rarely change direction from the initial to the objective state. Instead, systems change incrementally, one state at a time, from the initial state to the objective state. For instance, to achieve a function, a system might first change from some initial state to some resultant state, state B. State changes can be linked together such that the resultant state, state B, becomes the initial state from which another state, state C, results. In order to get from the initial state of a system to the objective state described in the function model, a series of states may need to be linked together this way. We can write the states as following one from another until we reach the objective state. The behavior models are always ordered in time this way. You'll note, however, that we have yet to provide explanations of the changes between states, only that state changes occur over time. For each state change, there must be some reason for that change, something that explains how the system changed from one state to another. Transitions provide the reasons or explanations for changes between states. For convenience, we label each transition in the initial and resultant state that it explains. Examples of explanations might be something like because of gravity, or because the switch is now on, or because part A is connected to part B, or because of the principle of cohesion, etc. Explanations come in a variety of forms, but these forms tend to be only of a few kinds, which we'll discuss later. By convention, we say that state A changes to state B by T sub 1, where T sub 1 is one of the kinds of explanation. It may also be the case that multiple simultaneous explanations may be necessary to describe why a state changes. Thus, in this abstract example, state B changes to state C by explanation T sub 2 and by explanation T sub 3. In this way, we can explain, step by step, exactly how a system accomplishes its intended function. Now let's go back to our example, the light bulb circuit. What are the meaningful states here? Electricity begins in the battery, which is our beginning state, or state 1. Electricity is then pumped by the battery to the switch. The descriptive value, location, has changed, so we create a new state, state 2. Next, an external force is applied to the switch, changing its mode to on. Again, a descriptive state has changed, so we create a new state, state 3. Now that the switch is on, the electricity can flow to the light bulb, changing its location again, requiring another state. Finally, the light bulb creates light, changing the real value of lumens from 0 to 30 foot candle, a change from 0, which requires a new state, state 5, which is our objective state. Note, it would be extremely cumbersome to note every single detail of a system in each state. By convention, we only show the values in a state that have changed or will be changing in the next state, rather than restating every value in the system. If we look at just those states we defined in the model, we can arrange them in order from state 1 to state 5, like so. This is the sequence of states in the behavior for which we'll next have to provide transitions. Until we know more about transitions, we'll just put in placeholders for now. Transition 1 to 2 will provide the explanation for why state 1 changes to state 2. Transition 2 to 3 will likewise provide the explanation for the change from state 2 to state 3, etc. In order to understand transitions, we have to understand something about the types of explanations that people usually use when talking about how a system changes from one state to another. There are 6 primary kinds of explanation that people typically provide for systems listed here. These are called transition or explanation types. We'll explain each transition type in the next few slides. Of particular importance is explanation by function, so we'll cover that one first. Transition by function. This indicates that the cause of the change of a system from one state to another is the result of a function of a subsystem of the current system. Because this is a very important type of explanation for SBF models, we're going to cover this one in some depth. The others will be more straightforward. Before we go further, let's revisit something we considered back in Lesson 1, the notion of systems and subsystems. Recall that a system is a group of objects that together accomplish some function. While a flashlight creates light, it also contains subsystems that accomplish additional functions that are necessary for the flashlight to create light. We call those additional functions subfunctions. For instance, the battery stores chemicals that are used to pump energy through wires in the flashlight. The battery is a subsystem of the flashlight system and accomplishes a subfunction for the flashlight to work. In this case, the subfunction is to pump energy through the closed circuit. Here again is our example of the light bulb circuit. Between state 1 and state 2, electricity moves from the battery to the switch. What is the explanation for this change? While there are a few possible answers, let's focus on the battery for the moment. The battery itself is a complex device within the light bulb circuit, which we call a subsystem. A subsystem is a set of structures, components, substances, and connections that are part of the overall system and that perform some other function within it. Just as we call the battery a subsystem, we call the function of the battery a subfunction. In the case of the battery subsystem, we say that the battery performs the subfunction of pump electricity. When we try to explain why the electricity moves from state 1 to state 2, we say it's because of the subfunction of the battery. We call this the bifunction explanation type. We use the bifunction explanation type whenever the state change can be explained by some subsystem and it has some very important implications for SBF. The reason for this is that a subfunction can be thought of like an entirely new function. I'm going to repeat this for emphasis. A subfunction can be thought of like an entirely new function. That means we can create an entirely new SBF model for the subsystem that performs it. So, SBF models contain explanations which can themselves be SBF models. Let's look at that another way. Here we show just the first 2 states for the light bulb circuit. In this case, we know there is a transition between states 1 and 2 with an explanation by function pump electricity. This explanation is a function itself, just like the create light function of the light bulb circuit. So we can define a new function, battery pumps electricity, which has its own beginning and objective states, which will match state 1 and state 2 of the create light behavior. And of course, this could have its own behavior structure model, etc. More abstractly, a transition, say between the states a plus 4 and a plus 5, could be explained by the function of a subsystem, in this case f2. Like all functions, the subfunction will have its own beginning state and objective state. The beginning and objective states of the subfunction f2 can be mapped to the state changes in the behavior a4 and a5 above. Note, we need not call the subfunction states by the same name, but we should be able to map the beginning and objective states of the subfunction to the states in f1 that the subfunction explains. We say that SBF models are hierarchically organized because a function can have subfunctions that help explain it. Those subfunctions can in turn have explanations which are also subfunctions, etc., etc. In this case, a behavior describing function f1, can have one or more subfunctions. Say 3 in this case, subfunction 1.1, 1.2, and 1.3. These can all be full SBF models themselves with their own behavior model and therefore their own subfunctions. The subfunctions explain in part how function 1 happens. Of course, subfunctions may in turn have their own explanations, which may be functions, creating yet more subfunctions. In this case, subfunction 1.2 has subfunctions 1.2.1 and 1.2.2. Explanation by function is one of the most important concepts for understanding SBF models. Explanation by function says a system changes from one state to another because of the function of a subsystem. This subsystem may be something like a battery in a flashlight, the power subsystem in a projector, or the transmission in a car. The function of that subsystem may itself be modeled by an SBF model, resulting in a hierarchically organized set of models. Thus, SBF models can be nested inside each other. It is explanation by function that enables SBF models to explain the behavior of very complex systems, one subsystem at a time. Next, we'll cover other explanation types. Explanation by principle is an explanation due to a fundamental principle or law, such as gravity or Newton's first law. Here we've listed a number of such principles. Such principles or laws usually require no further explanation and are often associated with an equation that provides more details. The cause of the state change of one structure occurs because of its connection to another structure. A door swivels open when a force is applied at the handle instead of falling over or just moving in the direction of the force because of the connection to the hinge. A piston proceeds linearly down the cylinder because it is aligned with and contained within the cylinder called a cylinder joint. Almost all state changes require a connection of some kind, so this is a very common explanation type. In fact, these connections are so common, they are often ignored in models or assumed. In this case, the explanation for the state of a state occurs simultaneously with and because of the transition of another. This is often the case in interconnected solid body systems such as gears, levers, joints, etc. For instance, in the upper picture with the gears, if the gear on the left rotates clockwise, the gear on the right will move counterclockwise simultaneously with and because of the movement of the gear on the left. Likewise, for the lower picture of the piston and crankshaft arrangement, the piston is forced down the cylinder. Because of and simultaneous with the transition of the piston from its original position to its new position, the connecting rod changes position. And because of and simultaneous with the connecting rod changing position, the crankshaft rotates. Notice, this isn't the only reason these systems work. Structural connections are likewise important explanations. For instance, the gear on the right will only move if it is also connected to the gear on the left. Let's take a closer look at the explanation by transition of the piston crankshaft arrangement. We break out the initial state into the initial states of the three separate components. This makes it easier to see what is happening. For the piston in initial state P1, its location is to the left. The crankshaft is located to the left at an angle of 0 degrees. The state of the crankshaft is at rotation angle of 0. An external stimulus, in this case an expansion of gas near the piston, causes it to move to the right. The transition P1 to P2 represents the period of movement of the piston from the left to the right. It is this period of movement, in other words, the transition P1 to P2, that causes the connecting rod to move. Likewise, the period of movement of the connecting rod, transition CR1 to CR2, is what causes the crankshaft to move. To be thorough, we should also add to our explanations the fact that the piston is connected to the cylinder, which has the function of constrains the movement of the piston, and that connecting rod moves because it is connected to the piston, and that the crankshaft moves because it is connected to the connecting rod. Often the achievement of some state by one component will change or allow the change of some state in another. This is an explanation by state. For example, when the switch is turned on in the flashlight, the electricity can move into the light bulb. The explanation for the flow of electricity is by state of the switch being on. Somewhere along the way, systems are typically acted upon by some external influence. We call these influences external stimuli, and when they cause a change in the state of our system, we say this is an explanation by external stimulus. In the case of the flashlight, light is not produced unless some force external to the flashlight system, such as that of my finger pressing the on-off button, closes the switch. For many systems, it is the influence of an external stimulus that starts the function in motion. As a quick review, we have just covered the 6 explanation types in an SBF model. Remember, explanation by function points to a subsystem within the system that in turn can be modeled by an SBF model, resulting in a hierarchical organization. Principles are fundamental concepts such as gravity or Newton's first law. Explanations by transition require simultaneous causal changes in states between two components, such as when two gears move. Explanations by structural connection are very common, often assumed, and occur because of the connection between two components. Explanations by state occur because of some state change in another component, such as the flipping of a switch. And finally, explanation by external stimulus provide a way to explain changes to a system that come from outside the system. Now that we know about explanation types, let's re-examine the light circuit behavior model. The light circuit model has 3 different kinds of explanation that are explicit. State 1 changes to state 2 because the function of the battery is to pump electricity. This is an explanation by function, which requires a subsystem like the battery. If we wanted, we could also create an SBF model of how the battery works. The function for the SBF model of the battery would be to pump electricity. State 2 changes to state 3 because an external force changed the switch from off to on. This is an explanation by external stimulus. some force external to the system, like a finger, push the switch from the off state to the on state. State 3 changes to state 4 because the switch mode is on, which is an explanation by state. The state of the switch is on, allowing the electricity to flow to the light bulb. Finally, state 4 changes to state 5 because the function of the light bulb is to create light and because electricity is now present in the light bulb. This transition involves two explanations. It is quite common for a transition to involve many explanation types. In fact, we could add to each of these transitions some explanations by structural connection, which are also necessary. For example, transition 1 to 2, the electricity could not move from the battery to the switch unless they were connected. Thus, we could add an explanation by the structural connection like so. Likewise, we could add to transition 3 to 4 connections between the switch and the light bulb like so. To review, the behavior models describe step by step the mechanisms for how a system accomplishes its function. A behavior model starts with the beginning state from the function and shows all the intervening states between the beginning and the final objective state. You can think of the behavior model as telling a story about how the system works. To tell the story, the behavior model uses two things, states and transitions. Just like the beginning and objective states in the function model, a state in the behavior model is a description of a system in terms of properties, values, and connections of the structural elements of that system for a snapshot in time. Whereas states describe the system in a point in time, transitions tell us why the system moves from one state to another. Using states and transitions, the behavior model tells the story of how the function changes the system from the initial state to the objective state. Furthermore, behavior models provide a higher order of organization to SBF models that allows very complex systems to be modeled through a series of interconnected SBF models. When explanations are functions of subsystems, they create a functional, hierarchically organized set of models. 5 other common explanation types are also possible.